Thank you for the invitation. It was actually thanks to Philippe, who spoke to me at the slag valorization symposium, and he said maybe it's interesting to present here. So I want to share some things we are doing in KU Leuven and the use of FactSage. We use FactSage mainly for producing cement alternatives. I think FactSage is more used for extraction of metals as an example, but I want to show you a bit of another side, more on the cement production and how it could be interesting to make actually a new type of cement, glass cements. So you will see then the presentation. So I just want to give first a bit a clear picture of why we are doing this, why we are focusing on new cement alternatives. So cement, you see that the use is all around us. It's one of man-made materials which is quite used a lot. Actually, if you use cement to make concrete, concrete is actually after water apparently the most consumed material in the world, which is quite big. And you see it in the numbers. So cement production is more than 4,200 million tons per year in production. And what is in cement is actually mainly Portland cement, is Portland clinker. And Portland clinker is actually an energy-intensive phase. It's composed of different mineral phases, which can react with water. But to make this phase, you actually have to calcine large amounts of limestone. So this results in a lot of CO2 emissions. So what has been done in the past is actually to reduce the amount of Portland clinker with various waste residues, fly ashes, blast furnace slags, calcined clays now being very popular, and then limestone to actually reduce the amount of Portland clinker while maintaining most of the properties, which is for concrete producers and cement producers, compressive strength. So there has been other research being done where I actually try to find alternatives which actually eliminate Portland clinker, but these are still, I would say, in their child shoes because they have some technical challenges. So we need quite a lot of supplementary cementitious. So can I go back? Yes. We're a bit too fast. Voilà. So we need a lot of supplementary cementitious materials to replace its Portland clinker, and there are quite some options out there. However, the most popular options, blast furnace slag and fly ash, are decreasing. Blast furnace simply is probably decreasing due to the electrical transition. The processes are being changed, for example, to electric arc furnaces. Fly ashes are decreasing because we don't combust that much coal. So we need actually new materials that can replace this Portland clinker, and actually in very high volumes, because the CO2 emissions are a bit unavoidable from Portland clinker production. So the more we can replace, the better. So therefore, slags and tailings come in the picture. They represent not that big volume compared to Portland cement, but every material can help to reduce the amount of Portland cement. But modification of steel slags, for example, is a hot topic where I will actually also talk about. So in this presentation, I want to put forward two options we mainly investigated in Leuven to form new cement substitutes, so these SCMs. And there are two case studies I want to present and how we use FactSage for that. So the first case study is that we do hot modification of slag. So we add something to the slag that makes it more amorphous after granulation and more reactive as a cement substitute. And then we have a second case which I want to present, and it's actually the use of tailings. Here in this case study, bauxite residue, to actually vitrify this material and to actually also cool this down very fast and create a Portland cement substitute. And actually these processes reduce the amount of CO2 emissions because actually you don't use that much limestone, and it's also quite interesting because you can valorize quite some byproducts which are now used in low-grade applications or even not used, for example, for bauxite residue. So the first case study is for electric arc furnace slags. So I want to thank Holcim and Nucor for sponsoring this work and also letting me share this. So just a brief overview for you have different routes to produce steel. A very popular electric route is the use of an electric arc furnace, which Nucor in the US is operating for all its plants. And basically, you take scrap, DRI, and some fluxes to produce steel and electric arc furnace. The slag now is actually taken out, tapped out, put in a slag pot, and that slag pot goes to the slag yard and dumps out the slag, and it cools down there. And what I basically do is you crush it up, you magnetically separate it to recover some remaining metals, and then you have a slag which has a very low value, mainly used as aggregate, and then that tiny bit of metal. So the question was, can we upgrade this, and how should we do this? And we proposed then a high temperature solution. But if you want to already screen some solutions, FactSage can be something nice to use. So there are different ways to produce upgraded slag, I would say. So we have the solution on the left side. So there actually you take the electric arc furnace slag, but you add reductants such as carbon. You can also use aluminium, like aluminium drosses can be something interesting to produce a metal. And there you actually extract the metal. You can capture chrome and vanadium. And then you have a slag which looks like blast furnace slag, actually a very easy route. Economically, this is a challenging aspect. The steel producers are not jumping for this because this costs a lot of money. So we were looking into a both more economical solution by just actually when they're pouring the slag out of the EAF, basically put additions to it, fluxes, so minor fluxes, basically that lower the liquidus temperature while keep actually the slag molten. So the melt temperature is dropping, but the liquidus temperature is dropping faster. So actually the material stays in a melt, in theory. And then you actually create this material, which can be an upgraded SCM. So one more aspect to introduce. So liquidus temperature is important for us because that determines the processing temperature, but also glass forming ability. We want to create something amorphous. And if you want to create a glass or amorphous structure, we basically have to cool our material very fast. And for steel slags, it's very difficult. It's very basic, so it crystallizes very easily. So we have to actually reduce the critical cooling rate. So the critical cooling rate is actually the rate at which you cannot form any crystals anymore. So if you put it in a TTT diagram, then that's the line on the left, which you have to obtain. Experimentally, this is difficult, but it can be done. But there's some nice work, a nice gem I discovered some time ago, a nice paper which was linking the critical cooling rate towards the viscosity and liquidus temperature. And basically you can imagine a bit as a glass making. A good glass is something that has a low liquidus temperature and a high viscosity, so a very viscous mix and a very low melting temperature. That's ideally to form a glass. Of course, with slags, going that viscous is not possible. You will not get out the slag of the slag pot, but this is an ideal scenario. So you can have a formula that was devised in that paper that actually you can calculate glass forming ability. So can you get these parameters from FactSage? Yes. So just using the equilib and also the viscosity model give you these parameters. We can also measure this at KU Leuven, but yeah, it's easier if you can calculate it much faster. So just something about the slag before going into the results. So this is I would say typical EAF slag. This is from Nucor, quite iron rich. If you look at the slag as is, it has very low amorphous content. And for the cement people, we would like to see that amorphous content higher, because amorphous most of the time means more reactivity. But of course, there are also some other minerals inside which can be interesting as they have latent hydraulic properties. However, for now, we focused on optimizing the amorphous content. So we used FactSage then to do some modeling. So basically, we added silica and alumina to increase or decrease the liquidus temperature. And we were checking what is now the effect on this liquidus temperature. So we saw silica and or alumina addition reduced liquidus temperature. Not so new yet. We did that also to see if the melt is freezing. If you add these additions, and actually after 2%, I think, more or less. All the additions you do lower the liquidus temperature much more than actually the melt itself. So in theory, the melt should not freeze when you add these additions. Then we can also model the glass forming ability. So the more bluish it is, the better the glass forming ability. So the lower the critical cooling rate you need. And basically we have seen if you add some additions, the critical cooling rate or the glass forming ability is becoming bluish, which is good. And I've plotted here for some residues we had produced in our labs, the amorphous content versus the viscosity over the liquidus temperature. And we actually see from a value of -6, you get close to 100% amorphous. And that's actually the target. However, we know it's very difficult with steel slags to do this. We have to add a lot of fluxes. So we will be somewhere around 60% amorphous. So around -7 to -6.5 with respect to glass forming ability. So we did these tests using this new parameter to guide us our experiments. So we chose some experiments which you saw as indicated on these heat maps. And we found out indeed that the more, if you add silicon alumina as predicted with that formula, you can create more amorphous content, and which is in line as what we expected based on our plots, that we could get around 60% amorphous. So then the final question is, which is for the cement people the most interesting, is it now working? Can you make it amorphous with these small additions, and is it actually reactive? And once we make mortars, ideally we have similar strength with respect to the Portland cement reference, and we tested this for 2 slags, and actually the optimum was for both slags the same, and we saw actually you can get strengths comparable to Portland cement. Surprisingly, because this material has a very different chemistry to the known SCMs, it's very iron-rich, and these iron-rich SCMs can be, for example, an alternative to blast furnace slag, as we see from performance. So I've done this case study also for other residues, for tailings, for example. One popular tailing or one voluminous tailing is bauxite residue, not so popular for the people living around these tailings. So the world production is quite big, 150 million tons per year, but again, with respect to cement, quite low. But locally, you have quite high volumes. They're scattered around Europe. There could be one tailing in your backyard, but maybe it's covered. And now, actually, these tailings are not really considered, not really used, because they're very alkaline, and they do not have really a specific use. They fall out of a lot of categories to be interesting as a raw material. So they are used in some cases as an iron and aluminium source. Depends if there's a Portland cement factory nearby, but for the rest, there's not much use so far. So we thought, and it's actually a proposal of my colleague, Tobias Hertel, like why not vitrify this residue to create also an iron-rich melt and actually create a new Portland cement substitute. So I've done this in pilot trials. So we have even made it at Technopark with Jan Urbanek, really making this material in a rotary kiln, which was an interesting experiment. But actually it was able to, although produce iron-reduced melt in a rotary kiln. It has quite some challenges, still not optimal, far from, but it was possible. So this was possible, but the question for you is, how did we use FactSage? So we calculated here 3 different items. Liquidus temperature, the lower the better, because we know at the Portland cement kiln we can go up to 1450 degrees Celsius. The lower we are, the better. We want to stay the maximum around 1300 degrees liquidus temperature. Amorphous content that we could calculate using the glass forming ability. There we want to be around 70 to 80%. We don't want 100% amorphous content because there are quite some heavy metals in the bauxite residue, chrome and vanadium, and we trap them in spinels. So we want some crystals, not too much because it will lower the activity, but it can help. And then the R3 heat, we could also predict that we use molecular dynamic simulation data and PDF, pair distribution function data. It's a bit more complicated, but we could also get an idea on what is the R3 heat. So you have seen the results of the pilot trial itself. We have some results still from another pilot trial, but the results are quite similar. So once we increase the amount of new SCM, that vitrified bauxite residue, we see actually that the strength is reduced, but not that much significantly, which is quite interesting. So although we have not that much Portland clinker, it can work. So this is something we have been doing, but we want to go further. And we got some money from KU Leuven to go a bit more into the scientific aspects of what we are doing. And together with Mathijs Schuurmans, we're trying now to data mine FactSage. It's a nice software. However, we want to do a lot of calculations, so we want to be a bit faster. So we want to mine it and actually to get these properties I was mentioning before. For example, in these, I made a simple model here with neural networks. And basically, we want to easily see what is the best or the closest chemistry if we have a certain, for example, residue, which additions we need to do, what would make sense. And the question to you, maybe for our coffee break, is we are also interested in latent and sensible heat calculation. I know you can get enthalpies and heat capacities from FactSage, but how to get to the real latent and sensible heat in an open system, yeah, that is interesting maybe to discuss. So I thank you on behalf of the team of KU Leuven. So this was at their last slag valorization symposium. If you have any questions, yeah,